All right, with Unit 2, let's look at some practice problems here. Question 1, which one of these is not a combination reaction? So combination, also sometimes called synthesis reactions, we're looking for a pattern. Now, unlike, and I'll talk about it over here, our redox or oxidation reduction reactions or combustion, where you're looking for specific things within the elements or within the molecules. So remember, redox, you're looking for something that is being reduced, which is gaining of electrons. And you're looking for oxidation, which is a substance to lose electrons. And these things have to happen simultaneously within one reaction. So you're not just looking for a reduction to occur, you're looking for both one substance in the reaction to lose electrons and a different substance to be gaining them. That's redox. My combustion, let me do this in a different color here. Combustion reactions, you're looking for something that, we'll just call it X, combines with oxygen to make carbon dioxide and water. And typically that X is some kind of hydrocarbon, which means it's a compound made up of hydrogens and carbons. That isn't necessarily the telltale sign. You're looking more for something mixing, reacting with oxygen, making carbon dioxide and water. So for these types of reactions, you are looking at the specific reactants and products. But for combination or also for decomposition reactions, you're looking for a pattern, not the specific element or compound. And so what is that pattern? Well, for combination, it's two or more reactants coming together to make one product. And those two or more reactants can be any series of things, really. I'm not going to balance these, but I'm going to give you some different examples. Oops. Okay, so notice on my reactant side, I have two, in these examples, just two reactants. And again, the reactants can be, diatomic substances, they can be compounds, they can be individual elements. It doesn't matter. You're looking for the plus sign between two or more reactants. And then the other big key, notice I'm making just one product. So can you take that and look at the 5 possible reactions up here, and let's decide what they are, just for practice, because I know some of your other problems might ask for decomposition or combustion. And then, in fact, before we do that, let's real quick define decomposition. Well, guess what? It's the opposite of combination. So you're taking one reactant and breaking it down into multiple products. And you don't even have to break it down all the way into A and B and C, all the individual elements. Again, it's the opposite. Instead of one product being formed, it's one reactant breaking apart into several pieces. Okay? All right, so let's go back up to the top here, and let's look at and label these 5 reactions. So in A, carbon plus oxygen makes carbon dioxide. Can you see what pattern that one has? Right, that's a combination. So that is a combination. How about in letter B, magnesium plus oxygen makes magnesium oxide, one product being formed from 2 reactants, combination. How about 3? Nitrogen plus hydrogen makes NH3, which is called ammonia, one product being formed, that's combination. Letter D, CaO, which is calcium oxide plus water, makes calcium hydroxide. Again, multiple reactants making one product, combination. So by default, you can probably guess what the right answer is, but let's talk about it anyways. This last one here, I have 2 reactants, methane and oxygen, making 2 products. So this is not combination. In fact, of the 4 reactions I've just talked about, this one fits this example here. And so it is a combustion reaction. All right, in this next one, we're going to look at formula weights, also sometimes called molar mass or molecular weight. The math all adds up the same. Molar mass would be in grams per mole. Get it? The mass of a mole. Same thing for molecular mass. Formula weight, formula mass, also sometimes called, see it's got lots of names, just has the units AMU instead, but the math is the same. So to do a formula weight, we need to look at the substance in question. So this is what's called ammonium sulfate. NH4 is the ammonium polyatomic ion. SO4 is the sulfate polyatomic ion. So its name, as you can see at the top up there, but the name is ammonium sulfate. Just some practice for you with naming. All right, so how do we decide what the formula weight is? So I need to figure out all the different elements within this compound, what they contribute, and then add them all up. So we have to look at a couple of things. We need quantity, and we need the mass from the periodic table. All right, so we'll do a little chart here like this. In fact, let's do one more column and we'll do a total here. Sorry, it's not very pretty. Okay, so nitrogen. Looking at this chemical formula, there's an invisible 1 here. 1 times 2, because remember the 2 outside gets applied to everything in the parentheses. So there's 2 nitrogens in this chemical formula. Can you see how many hydrogens there are? 2 times 4, total of 8. How many sulfurs? Well, the sulfate, even though I've drawn all around it, the sulfate, the SO4, doesn't have parentheses. It doesn't have any extra numbers on the outside. So there is truly just 1 sulfur from inside the sulfate ion, so 1 total in this molecule. And then oxygen, again, there's not parentheses with an extra quantity, so it's just O4, so my quantity is 4. Mass, I'm going to round to the nearest whole number, as it says here, to do that from the periodic table. Nitrogen has a mass of 14, hydrogen has a mass of 1, this is in AMUs. Sulfur has a mass of 32, and oxygen has a mass of 16. So we're going to have to multiply then. 2 times 14 is 28 AMU coming from the nitrogen. 8 times 1 is 8 AMU coming from the hydrogen. 1 times 32 is 32 AMU coming from the sulfur. And 4 times 16 is 64 AMU coming from oxygen. So that's what each of the individual elements contributes to the overall total. And when I add all of these up, the total, the grand total, is 132 AMU. And that's how you get formula weight. You would do it the same way for molar mass or molecular mass. It would just be that the units would be different. It would be 132 grams per mole. All right. Moving on to this next one. Of the species below, what is not an electrolyte? So remember, electrolytes, when you put them in solution, they separate into 2 ions. And again, I'm just using my generic A and B. Probably the best example is salt. Sodium chloride, for instance, separates into sodium and chloride ions when you put it into solution. So we're looking for things that are ionic, we're looking for acids, we're looking for bases. Whoops. These things all dissociate, which means separates, into ions when we're put into water. So HCl, that's an acid. It's going to separate into a proton and a chloride ion. So that is an electrolyte. It will give ions that when in solution will allow the electrons to flow and will light up a light bulb, for instance. Rubidium sulfate is the next one. Looks kind of crazy, but you've got a metal with your rubidium. And then you have sulfate, which is a polyatomic ion. So again, you've got an ionic compound, Ionic compounds separate into ions when put into water. So that is an electrolyte. Argon, just argon. Put that into water, if it'll even go, and guess what? Can that split apart into ions? No, that's it. That's all that's there. So argon is actually the answer, but let's keep going. Potassium hydroxide, KOH. I'm running out of room here, guys. KOH is a base. It's a strong base. Put it into water. You also have a metal in the polyatomic. Potassium ion and hydroxide ion splits apart into ions, which will be, in fact, a strong electrolyte when you put it into water. And then finally, sodium chloride I already talked about. Again, ionic compound, metal, sodium, non-metal chlorine. Put it into water, you get the ions. So letter C is the right answer. All right, and then last but not least, we've got a word problem here. A stock solution of HNO3 is prepared and found to contain 12.7 molar HNO3. Just going to write down my numbers as we go along here. If 25 mils of that solution, of that stock solution, is diluted to a final volume of 0.500 liters, what's the concentration of the diluted solution? All right, so we've got, this is concentrated, also called a stock solution, where you have a real big bottle of a concentrated solution, and you take a little bit of it and dilute it, and in fact you can make a lot more from that. All right, so this is my concentration and my volume of the concentrated solution, and I'm looking for the concentration of the dilute, knowing I have a volume of 0.50 liters. Now, what's consistent when we do a dilution? Well, that is the number of moles of solute remains the same, whether we're talking about the diluted or the concentrated. What changes when you dilute something? The water, the solvent. So think about really concentrated coffee and you want to dilute it, you can add some water to it and that dilutes it. The amount of coffee is still the same in there, but the concentration is different. Okay, so how do I get to moles of solute from this bit of information here? Well, keep in mind what molarity means. 12.7 molar means 12.7 moles of my solute, HNO3, per 1 liter solution. So if I had 1 liter of this stuff, I would have 12.7 moles. Well, I don't have 1 liter. I have 25 milliliters. Ooh, so somewhere off to the side, probably want to do one of those conversions. 1,000 milliliters equals 1 liter. So in fact, I have 0.025 liters of this solution. And when I work that out, notice what's left. Moles of my solute. Now, what am I looking for again? I'm looking for what the new concentration is. So when I solve for this number of moles here, I get 0.3175. So that many moles of solute were pulled out of this concentrated stock solution, put into a new container, and diluted to 0.500 liters. So I need to figure out what the molarity of the diluted solution is. Well, molarity, remember, is moles per volume in liters. And I know that the volume is 0.50 liters. So my new concentration, and definitely it's been diluted, is 0.635 molar. I started with 12.7. I ended up with 0.635. Yeah, that was diluted quite a bit. Now, I will also share a little shortcut with you guys. It's important to understand that your moles are the same, whether you have diluted or concentrated, but I can show you a little shortcut. Let me do that real quick before I wrap up. So there is a kind of a shortcut equation, and that is molarity, whoops, if I could do it right. Molarity of the diluted times volume of the diluted equals molarity of the concentrated times volume of the concentrated. Okay, and so what's happening, remember, is when I do molarity, moles per liter, times volume in liter, that leaves me with moles. And the same thing would be on both sides. Molarity, moles per liter, times volume in liters, would leave me with moles. So this equation here, this little shortcut, actually works quite well because, as we said, when you're diluting something, all you're doing is increasing the amount of solvent, changing the volume of the solution by adding solvent. Your number of moles always stays the same. So if we apply this shortcut, check it out. My molarity diluted in this problem, I don't know. My concentrated, or my volume diluted, is 0.5 liters. My molarity concentrated was 12.7. And here's the only thing you have to be careful of. Your volumes need to be the same unit because they're going to cancel. So this is in liters, this is in milliliters, and we converted the 25 milliliters a little bit ago. I just erased it, so let's assume we still know what that is. So there's that volume in liters. I want to solve for molarity of the diluted solution. So I'm going to divide both sides by 0.5 liters. And guess what? When you do the math, you get the exact same answer. All right, so there you go, guys.